And the agenda for today is we'll be delving into a lot of details of UL 3741 solutions. We'll start with a brief history of the standard to set the stage for our discussion on SolarEdge's PV hazard control solution, which aligns with these standards. And then we will be examining how not all UL 3741 solutions are created equal, and focusing on some key topics that you see here, such as safety, design flexibility, balance of system analysis, energy production, as well as some O&M comparisons. So between Jacob and me, we'll go through some of those topics, and lastly, we'll wrap up with some Q&A, where you'll have the opportunity to ask any questions that you might have on this topic and the presentation. So without further ado, let's dive into the history of the UL 3741 standard with Jacob. Jacob, over to you.
All right. Thank you, Varsha, and thanks, Julia. Welcome, everyone, to our webinar today. So as Varsha mentioned, I'm going to start with a brief history of the 3741 standard. 3741 was introduced in the 2020 electrical code as a new option for controlling voltages inside of the PV array. So as with previous versions of the code, the voltage outside of the array is needing to be brought down below 30 volts within 30 seconds upon the initiation of rapid shutdown. But now, with the introduction of 3741, anywhere within 1 foot of the projection of the array boundary, voltages can either be brought down below 80 volts or use what's called a PV hazard control system as defined by this UL standard to control voltages within the array. So to take a closer look at some versions of PV hazard control systems, these systems can be comprised of a single piece of equipment or multiple coordinated pieces that perform the function of reducing electric shock risk for firefighters. Some 3741 listed hazard control systems are designed to work with up to 1,000 volts DC still present in the array. And what we've seen in the market recently is a number of racking manufacturers have listed solutions that require placing the inverter within 1 foot of the array boundary and using specialized mechanical protective devices to reduce the likelihood of firefighter interaction with energy sources that are inside of the array. So these solutions require the coordination of many parts and a specific set of listed inverters, modules, wireways, and even zip ties all work in coordination to create the PV hazard control system. Having the inverter's DC connection within 1 foot of the main array allows DC cabling, all DC cabling, to be part of the hazard control system and not subject to the 30 volts within 30 seconds rule. For every racking solution to 3741, any disconnected subarray, that means greater than 2 feet distance between that portion of the array and the main array, is required to use module level rapid shutdown or listed PV rapid shutdown equipment to maintain voltages below 30 volts at those crossing points. So now I want to take a quick look at SolarEdge PV hazard control system under UL 3741. So this case, the entire listing is comprised of just power optimizers paired with inverters. So it is listed and compliant with the National Electrical Code with any module and any racking. So when RSD is initiated, the rapid shutdown, optimizers will drop voltage automatically to an output of 1 volt DC each. And that's actually removing hazardous energy from within the PV array. And because those energy sources are essentially removed or brought down to low levels, there is no requirement for special racking, raceways, or wire management. So with that sort of background of the situation of 3741, we want to open up a poll for the group here.
Thanks, Jacob. Yeah, we want to move to the next segment of this presentation where we want to make it more interactive, put some questions out there, see what you think, and then we'll go through some key differentiators between the different UL 3741 solutions. So let me launch this poll here. Please take a few seconds to review it. Just a couple more seconds. Stay. All right, I think we have enough answers here. I'm going to close the poll. Okay, let's take a look at those results here. So it looks like a lot of you said that the safety can vary. That is absolutely true. And this is where we'll go through the next few slides with you to showcase how that happens. So next slide, please, Jacob. So yeah, take a look at this table. This is directly from the UL 3741 standards document. And this helps us gauge the risk levels for firefighters when dealing with PV systems. So if you look at the array voltage levels of a solar array, they correspond to specific hazard levels. And this factors in the resistance of a firefighter's gear, wet or dry. And you'll see that there's minor effects like tingling at lower voltages, but that quickly escalates to life-threatening at higher voltages exceeding 600 volts DC. So our systems, which is specifically the DC optimized solutions, typically register at hazard level 1 or below, indicating minimal risk. But it's important to note that the DC voltages can be as high as 1000 volts DC for traditional string inverters without non-MLPE, without MLPE included as part of the solution. And this is categorized as the maximum hazard level 3 or below, which indicates a significantly higher level of danger. And thus, this is where it's going to be a little unsafe. It's starting to get very unsafe for people going up on the roof. So let's take a look at the next slide. So this is where we're looking at control voltages of non-DC optimized systems. So if you take a look at the inverters here, it is within 1 foot of the array, and it has 1000 volts DC within the array. And this is, like we looked at the previous slide, it's within that hazard level 3 for the standards. So this basically highlights that there is stringent cable management required in racking systems when you're dealing with such high DC voltage. And of course, you'll need exterior mechanical parts to ensure that there's precise cable management techniques that are required in order to maintain safety with such high voltages. In contrast, you'll see in the next slide here that a DC optimized system typically operates at lower voltages, and it reduces the need for such extensive measures like zip ties and exterior components. So take a look at the controlling voltage here. So we have 125 volts DC input to the optimizer, which typically links 2 panels in series. And from a single panel, we can see an output of 60 volts. And after rapid shutdown, each optimizer reduces its output to just 1 volt DC. So the output for an entire string of optimizer is brought down to 30 volts. This means that the maximum voltage you would encounter anywhere in a SolarEdge system post rapid shutdown is 125 volts DC. And this, of course, the control level voltage responds to the hazard level of 1, according to the table, which is the major safety advantage of a DC optimized system. So in the event of an emergency, these low voltages are critical for the safety of first responders and maintenance personnel and anybody else who gets on the roof. So going to the next slide, we wanted to do just a side-by-side to show the safety enhancements that come with DC optimization. So looking at the desired behaviors that are required for a safe and secure system, a critical safety feature is the automatic shutdown of deadly electricity. So this is where SolarEdge systems excel by being able to reliably initiate shutdowns. So in the event of an emergency, the high voltage can be reduced or shut off entirely, safeguarding not just firefighters, like I mentioned, but also O&M personnel, roofers, and anybody who regularly works with the system on the roof. And this feature is absent in non-optimized setups. There is also the daily self-RST tests that are conducted by DC optimized systems automatically, and these are able to affirm compliance and reduce liabilities by catching errors that could otherwise lead to safety concerns or system failures in the long run. And this automatic operation eliminates the dependencies that non-DC optimized systems, for instance, have on other components. So with us, you're trying to ensure a robust fail-safe mechanism, even in the event of installation errors. Moreover, the DC optimized system removes the need for regular inspections to confirm compliance because they do not need the mechanical protective measures. So it's clear that, with SolarEdge, we're not just trying to meet the standards of this, but we're trying to exceed them. And we're providing a safety net that goes above and beyond, and is trying to cover all individuals interacting with the system beyond what is typically expected. Next slide, please, Jacob. So just to end on the safety aspect, I wanted to show how SolarEdge takes a holistic approach to PV system safety, and it's intricately designed around these three core principles: prevention, detection, and mitigation. So the solutions with optimizers are able to identify any early signs of electric arcs at the module level through SenseConnect, built-in temperature sensors, and daily RST self-tests. So prevention is our first line of defense there. And for detection, the system is equipped with arc fault circuit interruption and system alerts down to the module level to detect arcs and report errors. So situations are managed by O&M professionals swiftly. And in terms of mitigation, as you can see, we do have built-in safe DC and rapid shutdown protocols that are automatically triggered in case of an emergency to minimize risk. And together, the inverters and the optimizers here are working seamlessly for early detection of potential arc faults and monitoring down to each individual PV module. So this, something to highlight is this does meet the engineering requirements that are recommended by leading property insurance companies, including FM Global and Zurich. So SolarEdge continues, to educate the industry on the importance of PV system safety, and we continue to live by the principle of safety by design. With SolarEdge, we want to have a proactive safety approach, not reactive. With safety being integrated into every aspect of our product design and functionality. I wanted to mention something that stuck with me when a customer in one of the previous webinars on UL 3741 mentioned in the context of the standard. He just said, why would we want to compromise the safety of the fire department and of the people inside the building with something that's inherently less safe? Right, because just the thought of the system, he mentioned just being installed on, let's say, even a school, right, where someone accidentally stepped on a wire on the roof. It could be a child, it could be somebody else who got on the roof by mistake, but that caused an arc fault or ground fault. That is pretty unsettling. So he just said, he wants to have the peace of mind that comes with the module level safety controls that will definitely ensure the safety of the property and personnel. Okay, so with that, I want to go to the next section where we have another poll question for you. We wanted to see what you think about design flexibility. How does the UL 3741 solutions without MLPE impact PV system design? So if you can take a look at it very quickly. We'll give it another 20 seconds. Okay, I think we have about 50% voted here. All right, let me share the results. All right, take a look at the results here. So looks like 50%, about 50% said that it would limit design options due to increased complexity. So let's see how that actually works in reality. I think most of you got it right, because you do know that it's going to be a little different, right, in terms of constraints. So let's look at a non-DC optimized solution here on the roof with a 300 kilowatt system. Jacob, next slide, please. Okay, here we go. So looking at the imager, this is just an aerial view of a 300 kilowatt rooftop solar installation using traditional string that doesn't include built-in MLPEs. So this is, if you look at the blue squares, those are the various inverters positioned across the rooftop. And the placement of these throughout the area and distributing across the roof requires additional structural engineering work that complicates the installation process overall. And moreover, the PV RSC and the red circles that you see is the string isolation devices. And these are required on most of the subarrays here with a non-DC optimized solution. And these devices are, of course, crucial to remain compliant with the RSC regulations, as you know. And they're required to de-energize in case of an emergency. But the extensive use of this, increases the complexity and increases the need for additional equipment when DC optimization isn't employed, which can again have implications for both the initial setup as well as the long-term maintenance of the system. So the inverter placement is constrained, as Jacob mentioned in the beginning, to within a foot of the array. So there's a loss of installation flexibility. You cannot install panels everywhere, and there's also potential shading issues that you may run into. And any subarrays or alienated arrays that are by themselves on the side of the roof will still need additional MLP to comply with the regulations, or they must be repositioned closer to the main inverter, and that complicates the setup. So if we take a look at the next slide, where we have a DC optimized system with the same setup, 300 kilowatt, you'll see here that the inverters are just centralized, located in one space on the roof. And this overall just streamlines design, right? Simplifies installation, maintenance, as all the critical electrical components are accessible in one portion of the roof. And again, because we have built-in DC optimizers on the panels, we do not need the additional PV rapid shutdown components as well. And an important thing to note is that the system compliance isn't compromised by the inverter placement. So you could effectively install the inverters at a ground level, or you could put them on the roof wherever it's necessary for the design, and it offers further flexibility for the whole design as a whole. And mounting inverters at a ground level essentially eliminates the need for costly structural reinforcements that are usually required with rooftop installations. So this not only simplifies the entire process, but also saves money by avoiding the need for additional, more complex reinforcement measures. And also, Jacob will go through in just a bit that positioning inverters on the ground can have significant cost reduction on the AC, balance of system cabling. So he will cover that in more detail, so we'll get to that. But just to summarize, our design flexibility overall, because of DC optimization, you can easily put the inverters in a central location on the roof or ground placement for shorter AC runs, maximizing savings and serviceability, and without compromising efficiency. There are no extra components required on the roof because of built-in rapid shutdown and safe DC, which means less complexity, lower costs again. And then lastly, you can install larger systems easily because you don't have to put inverter within 1 foot of the array, and you don't have to worry about the subarrays and the alienated arrays. So you're able to essentially maximize and use the whole rooftop potential to install larger systems. Okay, so with that, let me pass it to Jacob. There is another poll question that we're going to toss it out there. So please take a look. Okay, Jacob, kicking it back to you.
All right, thanks, Varsha. So yeah, let's open up this next poll question. I feel like this is one of the biggest topics when it comes to 3741, and that is, what's the cost impact of being able to exclude MLPEs from a solar system on a rooftop. So we'll give everyone just a little bit of time to submit their answers here.
I think just a couple more seconds. I think we'll have about 50% or more. All right, let me throw up the results here for you, Jacob.
Okay, great. So yeah, we're seeing a mix of opinions here. For the most part, there's an expectation that you're going to reduce costs by excluding MLPEs from a solar system. So great. This is exactly the perception that we kind of want to talk about. Is my screen still visible, Varsha?
I think we'll just have to close the survey here. Let's make sure. There we go.
Cool.
Yep, it's back.
So we'll move a little bit away from the safety and compliance discussion now and talk, some more dollars and cents here. As you might expect, removing MLPEs from the rooftop is a big cost-saving opportunity. And we at SolarEdge obviously wanted to take a closer look at those claims. So what we've done is we've taken 5 typical rooftop C&I solar systems of various sizes and looked at 2 design variations to be UL 3741 compliant. So one, of course, using a SolarEdge DC optimized solution, and one using a non-DC optimized racking solution. And I want to note that the comparison methods and results here have been independently reviewed by Pure Power Engineering Group. What we've determined over 5 different case studies is that savings on the balance of system are pretty consistent across the spectrum when using a SolarEdge DC optimized solution, and up to even over 50% savings as possible on the balance of system. And there's a few reasons for that. Traditionally, DC optimization allows for longer DC strings. So if you could put up to 60 panels in a single string, where traditional string inverters might allow up to 20, depending on the module, DC optimization is lowering your string count, up to 67% in some cases. So there's a lot of savings there. In systems that are using racking solutions for 3741 compliance, there are additional reasons beyond that balance of system costs can increase. At the heart of these is design flexibility. So string inverters needing to be installed within 1 foot of the array means that inverters can't be centralized and they can't be installed at a ground level. So the AC costs for running AC cabling from your inverters to your AC combiners or other AC switchgear is going to be a lot more expensive. So these cables often need to be oversized to keep resistance losses low because they're going to be much longer. On the other hand, on the right side of this image, you can see SolarEdge systems allow for installations of the inverter in a centralized location, ground level, or on the roof, and using aluminum cables on the DC side in a combined format can be even further cost reduction. So when we look at these 2 design variants head to head, we can see, the AC cabling from inverter to combiner, from combiner to interconnect is going to be much more expensive in both materials and labor for a non-DC optimized solution. And when we take an average across all the case studies that we've analyzed, we estimate that the costs for strictly AC cabling, conduit, grounding, and install labor of all those pieces can account for an increased cost of up to 5 cents a watt. So another piece of increased cost for a non-DC optimized solution is the addition of MLPEs or PV rapid shutdown equipment to parts of the array. So while it is possible to avoid the use of these entirely in some smaller rooftops, it's quite rare to have a C&I rooftop without at least a few breaks in the array, given fire code requirements for walkways or rooftop obstructions. So one option available is to use MLPEs, rapid shutdown devices, at the module level on portion of the rooftop. So any module that's connected to an inverter in a different array. The image here shows how modules that are connected across a gap between two arrays all require some type of RSD at the module level. So all of the modules shown in blue are actually connected to MLPEs in this PV system. All of the modules shown in white are without MLPE. And the other option for non-DC optimized solution is to use PV rapid shutdown equipment, devices, whenever strings cross the gap between subarrays. So as shown in this image, 1 to 2 of these devices is going to be needed as a rule of thumb per subarray. And when we look at an average across all the case studies of varying sizes, we estimate that the material and labor costs for adding these devices, either the rapid shutdown equipment or the MLPEs, can account for an increased average cost of 1 cent per watt DC. So back to the elephant in the room. Balance of system savings are great, but the big question is, can they make up for the cost, the equipment cost of MLPEs or not having to use MLPEs? So what we've done is take a market research average of about 7 cents per watt for the cost of inverter equipment. This comes from NREL. And we can put together a final estimate of all capital expenses, all CapEx costs, including the price of equipment, inverters, and MLPEs were used, the balance of systems cost, and the direct labor costs. And what we see is that for DC optimized and non-DC optimized solutions, we're very close in costs. And in fact, for the 5 projects that we analyzed in this scenario, 3 of the 5 systems were actually more expensive from strictly CapEx perspective for non-DC optimized racking solutions. Of course, there's going to be some amount of variance. This depends a lot on the size of the rooftop, how it's laid out on the roof, and what strategies are going to be used for rapid shutdown compliance. But it's important to note that it may well have, the overall cost may well be in favor of using DC optimized solutions. So let's take a look at another piece of system cost, and that is, I guess, the other side, and that's the revenue. All PV panels experience mismatch, causing power losses and dragging down system performance. There's a variety of reasons that mismatch occurs, but it tends to get worse over system lifespan. So soiling, manufacturing differences, all of these things can increase over the lifespan of a system. In a traditional stringed PV system, one module producing less energy due to mismatch can affect the production of the entire string. And with a DC optimized topology, these power losses are going to be mitigated because the maximum power point tracking is performed at the optimizer or pair of optimizers level. And this is going to create additional flexibility in the design. You can install more panels at different angles, inconsistent shading, and bifacial panels are going to produce better as well. So using SolarEdge inverters and optimizers to reduce power losses means that your system is going to produce more energy over the lifetime and produce greater revenues for the system owner. So for those same 5 projects, we run an energy analysis via PVsyst, and what we see is that the revenue over the lifetime of a system in net value can be up to 5% higher for the life of the project. And that translates to around 7 cents per watt increase in revenue for the system. So we're going to open up one more poll here for the group to talk about operations and maintenance. Varsha, if you wouldn't mind opening up that poll. The question is basically, which of these practices, select all that apply, are going to be used for streamlined O&M of any solar system.
Give it another 10 seconds. I think we have about 40% voted. Okay, all right, Jacob, I'm going to close this out. We have about 55%.
Great.
Let's take a look. There we go.
Okay, very good. So yeah, we see all of these practices are getting used to a varying degree. Interesting to me is that the compliance inspection, consistent compliance inspection, is actually being done, the most often out of these four. So, excuse me. This reason I find that interesting is that it's important to understand that compliance inspection actually only occurs once for most PV systems, and that's at the time of interconnection. So one of the big concerns for 3741 systems that use mechanical protective devices like zip ties and plastic raceways is that there's not really a way to know if these components have failed, if it's from weather or just over time, without having a visual inspection of some type. So this means that a system can fall out of compliance with the NEC rapid shutdown requirements, and at that point it's no longer providing the proper protection for firefighters, and all of that's happening without the knowledge of your system stakeholders. Unfortunately, practices like IV curve tracing or drone flyovers aren't detecting issues ahead of time. And for that reason, what we think would be recommended is at least 1-year checks of the protective components to make sure that they are maintaining protection for firefighters. And interestingly, it looks like about 67% of those who answered in the poll would tend to agree. With a DC optimized solution, you actually can access live site data from the optimizers and the inverters at all times through our free online monitoring portal. So all of these features are available with module level monitoring. Any issue in the site can be alerted to as soon as it occurs. So rapid shutdown functionality is going to go through a daily automated test. And what's more is that any site fault is going to trigger an automatic shutdown of the affected optimizer, string, or inverter, meaning that the system is always going to remain compliant with the rapid shutdown requirements after install and commissioning. So all of these included features means that systems without DC optimization are going to have increased O&M costs for the additional practices. The practices that we just mentioned earlier, IV curve inspection, infrared scanning, annual drone inspection, inspections for array safety compliance, all of these have costs associated to them. And what we've done is try to estimate what these costs are in conversations with O&M providers. So for some of these practices that are used only when issues are present in the array, the cost is going to be less during those middle years of a system where it's just experiencing less issues, as opposed to the early life and end of life of a system where you're going to have more issues. So a bathtub curve was used to model the expected total cost of additional O&M tasks for a non-DC optimized solution. And the number we came to was about 6 cents per watt DC over the lifetime of that system. That's in today's dollars. So what you can see is when we take a look at that original CapEx side-by-side estimate, and we add on top of that the estimate of additional O&M costs for the lifespan of a non-DC optimized system, overall system costs can lean even more heavily in favor of utilizing DC optimized solutions. And then when we add that final piece we discussed earlier, which is the expected difference in energy revenues, you can see that the economics of DC optimized solutions are quite preferable to that of non-DC optimized solutions. So just to summarize, the main benefits that we've been talking about for the past 30 or so, 40 maybe minutes here. Number one is that, safety. By reducing voltage to touch safe levels upon any fault or any maintenance, you're getting an enhanced safety as opposed to using passive mechanical components that are protecting these hazards by covering them. On the balance of system side, up to 50% savings of BOS is possible by reducing the number of DC strings, decreasing the length of AC cable runs, and avoiding the use of additional accessories for hazard controls. On the energy production side, increased energy revenues of up to 5% over the system lifespan. O&M, reducing costs by leveraging the web-based real-time monitoring at optimizer level. And finally, just design flexibility, inverters being installed centralized or at a ground level. All of these are options. The array can be broken into more sub-arrays, more rooftop space can be maximized without having to add additional rapid shutdown equipment. So I'll pass it over to Varsha to talk about some of the additional resources we have on this topic for all of you to access.
Thank you, Jacob. So yeah, we just wanted to say, don't just take our word for it. Use some of these resources that we have here on the slide. There is a white paper that I mentioned in the beginning that Jacob helped author, but it has been validated by a third-party engineering firm that Jacob mentioned, Pure Power. So be sure to take a look at that. There's an application note that we have, and there's also a couple of articles that Solar Power World and PV Magazine have published on this topic. So do review those, and we'll send you the infographic as well. So just a reminder, feel free to put your questions into the questions chat if you haven't already, and then we will, as part of our post-event email next week, we'll send you this recording along with some of these resources that we mentioned. So you'll have everything handy in there. So with that, let's start going through some of the Q&A and open the platform for questions. So Jacob, do you want to go to the next slide? Maybe keep it on there. I will open up some of the questions here. Okay, lots coming in. We'll try to get to each of these in the 15 minutes we have. Okay, so Jacob, there is a question from Chris. How does SolarEdge's RSS 690.12 solution differ from the UL 3741 offering, or are they the same thing? Wait, you're on mute.
My apologies. So good question. A UL 3741 offering is a solution for 690.12. So if you go and look at 690.12, one of the options listed under it is 3741. And I think actually, Chris, your next question is getting at the meat here, which is if you've already got an optimizer, why do you need a 3741 listing? And the threshold there is that 80 volt threshold. So for a one-to-one optimizer scenario, voltages in your array are going to be below 80 volts. So it actually falls into one of the other options under 690.12. For a 2-to-1 optimizer connection, you'll have two modules in series. Those voltages can go above 80 volts. And that's where the 3741 compliance is the solution for 690.12 requirements instead of just below that 80 volt threshold.
Got it. Thanks, Jacob. There's another question by Peter to explain the additional structural requirements that are required with the non-DC optimized solution.
Oh, sure. So basically protective raceways, specialized zip ties or cable clips to maintain a certain amount of spacing from your home run strings to the conductive parts of the racking system, things like that. I would definitely recommend looking into some of the manufacturers of racking systems that have listed under UL 3741, and you can check out all of the different strategies being used for essentially specialized cable management.
Perfect. One more question here is, do string isolation devices need to be UL listed along with the racking system?
String isolation devices, as far as I know, they don't need to be listed with the racking system, but they need to be listed under 1741, PV as listed PV rapid shutdown equipment.
Got it. Okay. Yeah, a few questions here on whether we're sharing the deck and the recording. Yes, we'll put a PDF of the deck as well as a recording for you in a future communication going out next week. Another question is, how long do these safety critical wire management parts that are required for the code compliance, such as the plastic ties that we were showing, expected to last? Jacob, maybe I can touch on that and correct me if I'm wrong, but it depends on the weather, of course, but it's 2 to 3 years according to the racking manufacturers. Let's see, there's more coming in. So what's the cost of buying and installing MLPE, part of the BOS cost calculations, Jacob?
Yes, that's an included cost when we look at the overall balance of systems. For balance of systems, the install labor for installing MLPEs is included, and then when we look at CapEx, which is slightly more broad, the equipment cost of those MLPEs is also included.
Gotcha. Thanks. And there was an NROL report, I guess, that you were referring to in the slide deck. So John is asking which NROL report was that?
Testing my memory. It is referenced, I think it's a 2022 report from NREL. It's referenced in the white paper that we've linked to, so definitely go check out that white paper. And down in the sources cited section, that NREL report is listed, but it's from 2022, I believe.
Mm-hmm. Yeah, and I'll just comment again and say that we will have the white paper sent to you so you can read it at your leisure. And then there's an interesting question here from Kyle. Do any panels come with built-in rapid shutdown?
It's a good question. I'm not aware of that on the market, or at least not being a major share of the market.
Yeah, Kyle, both of us aren't aware of it, but we will look into it just to get back to you on that. Let's see, there is a question from David here. Does SolarEdge have crosstalk issues? And I know that Kleber is the expert on this topic. So Kleber, in case you're here and you want to address that, feel free to jump in.
Sure. Hi, hello everyone. Yes, absolutely. So the crosstalk, we do not experience crosstalk because of the way that we designed and we're certified as a system between the inverters and the DC optimizers. So every time, so every time that the inverters and the DC optimizers are paired together, they have its own, each DC optimizer has its own signature. And in fact, we're going to be a few days away to release a white paper on that, an application note, explaining the fact that we do not suffer from crosstalk. Okay, and other solutions out there, they are not. Since they are not designed and certified as a system, they do not have this on signature for HDC optimizers.
Got it. Thank you, Kleber. Jumping in, Jacob, couple more questions here. So does SolarEdge have any material that's available online that I could provide to fire inspectors upon post-installation inspections for compliance with the standard?
I would definitely recommend they check out the resources, specifically the application note that you linked previously. the application note basically describes the differences in meeting 3741 for a solar edge solution or a non-solar edge solution. How is that done? So definitely worth checking that out.
Yeah, and just to add to what Jacob said, I do believe that our 3-phase product installation manuals along with app notes will contain the required instructions. So just take a look at that. Let's see, more questions coming in. I think we got through almost everything.
Varsha, there is a question about zip ties. There is a question about zip ties that I think would be good for us to cover. I'm not sure if you covered that one.
Oh yes, let me make sure I cover that.
From
John's
John.
question. Yes. You can use zip ties on UL 3741 systems. All wiring management must be UL listed and non-conductive. Why look at a tracker when UL 3741 is a rooftop thing? That's the question. Yeah. Thanks for catching that.
Good question, John. So I would encourage you to check out some of the listings of different racking manufacturers for UL 3741. There are definitely a few of them out there, with 3741 listings that are using zip ties as an integral piece of the wire management and essentially maintaining certain gapping distances from conductive parts of the racking to the cabling within the array. So I would recommend, definitely checking that out.
And just to address the second part of the question with regards to why we put the tracker, right? I mean, the picture there, the tracker, that's just as an example. We are not saying that there's trackers on rooftop. That was an example that actually I visited that plant, at the location where it's a ground mount, and that plant was 2 years old, and we saw the picture there. You see that zip ties, they'll break after a year or 2 or 3 years old, 3 years in the field. So it's just a fact, right? I mean, that if you're putting the safety of your PV, of your rooftop, on zip ties, cable zip ties, plastic ties, that's what can happen.
Yeah, thanks, Clever. I see a comment from Susan. Susan says Hellerman Titan ties are designed to last 25 years. Yeah, thanks for that comment, Susan. Yeah,
it's a good point. And there are zip ties that are listed with some of these systems that have, ratings for longer lifespan. What I would note is that the warranty level on these ties is still usually between 1 and 3 years. So just something to note. And obviously, the concern that we have with zip ties is that you don't know when they break. There's no way to actually know that without going to site and checking in person.
Yep. And that's why we mentioned that it's tough to maintain that compliance over the years without checking that they're, indeed lasting for that system lifetime. There's one more question from Patrick. Does SolarEdge offer an external RSD push button? We've had some AHJs asking for this.
So the answer, there are ways to have, external control of your rapid shutdown. So I would recommend, Patrick, reach out to one of us and we can point you in the right direction there. There are definitely options for getting external buttons or disconnect switches to initiate rapid shutdown.
Thanks, Jacob. I think one last question. With the need for automatic mid-circuit interrupters and a few manufacturers making these, will there be guidance on standardizing these non-module level devices, including any sort of communication standard, such as SunSpec?
Sorry, would you repeat that question for us, Varsha?
Yes, sorry, Jacob, I'll go slow. So it says with the need for automatic mid-circuit interrupters and a few manufacturers making these, will there be guidance on standardizing these non-module level devices, including any sort of communication standard, such as SunSpec?
Okay, good question. So 3741 is the standard that applies to mid-circuit interrupters within the array. So that's essentially what a 2-to-1 optimizer is doing. It's interrupting every 2 modules. For devices between arrays, the PV rapid shutdown equipment, the standard for that is 1741. And so for the entire rapid shutdown system, which is your inverters, your PV RSC under 1741, your 3741 solution, the coordinated operation of all of that is checked as part of your NEC inspection. So check with your racking manufacturers. Some solutions need many coordinated devices from different manufacturers. The SolarEdge solution is fully covered just by having the optimizers and inverters there. The Sun spec part of that question, that's an optional communication standard for OEMs to comply with. So I wouldn't expect that to be within the National Electric Code anytime soon.
Thanks, Jacob. We'll take maybe one more question here. So firefighters are used to expecting 80 volts within the array, and now with 1000 volts allowed, how would they know the difference, and are there any signs? This is an interesting one because during a fire situation, it's almost impossible to tell the difference. So you wouldn't know what the voltage in the array is after rapid shutdown is activated, and there are no additional signs within the array level. So this is definitely a gap in the code that needs to be addressed. So I'll leave it at that. Let me see any more questions here. RSD. Okay, I think that's everything. I'm hoping I didn't miss anything. Yeah, if we have, we'll go through and make sure we get back to you in the next week or so. So just keep that in mind. And we will, of course, send this deck and the webinar recording with some resources like we mentioned. So thank you so much, Kranich and Julia, for hosting us. And thank you, Jacob and Kleber, for being here and for your time. Thanks everyone, for your business.
Thank you, everyone.
Have a good one.
Bye.
Take care.